AI is the engine driving, well, our entire economy right now, isn't it? We talk constantly about the amazing capabilities of these models, the speed, how they're changing everything.
Everything from medicine to art.
Exactly. But there is this massive hidden cost we rarely discuss. The resource hunger. I mean, the sheer staggering demand for electrical power and cooling.
It's immense. And terrestrial data centers, even the most efficient ones, are rapidly bumping up against, physical limits. Where do you find the land, the grid access, and millions of gallons of water all in one place?
Right.
And this pressure has pushed researchers to propose something. Well, something truly revolutionary, launching entire AI data centers into orbit.
A completely self-contained floating compute cluster. I mean, it sounds like pure science fiction, but the sources we're looking at today suggest it's an engineering path being seriously considered.
Yeah, and we're talking about putting them in a very specific place. Sun-synchronous low Earth orbit, that orbit is the key. It allows the satellite to constantly track the sun.
So it's always in the daylight.
Always. The core idea is simple, really. Use 24/7 sunlight for free power and the naturally freezing cold vacuum of space for effortless cooling.
Okay, so here's the mission for this deep dive. For you listening and for us, is this vision of space-based compute a futuristic fantasy? Or is it a practical, maybe even cost-effective alternative to what we have on the ground?
And this is where we have to hit the central conflict right away. The sources are crystal clear. This solution comes with a staggering financial hurdle.
A staggering one.
We're talking about a capital expenditure, a CapEx, that's currently estimated at 5 to 10 times higher than a conventional data center for the same power.
5 to 10 times. That is the massive premium we have to get our heads around. So what operational benefit, what strategic advantage could possibly justify that kind of expense? Let's start with the operational upsides. Why would you go through all that hassle to move these things off planet?
Well, it really boils down to eliminating the two largest ongoing costs for terrestrial centers, power and cooling. The operational expenses, or OpEx, are just radically reduced.
Okay, so lay out the mechanics for us. Why is ILEO the ultimate power solution?
Because of that sun-synchronous orbit we mentioned, by staying constantly lit, these centers can achieve a power duty cycle greater than 90%.
Greater than 90%.
So you have practically continuous renewable sunlight, no need for fossil fuel backup generators, zero carbon emission penalties, and, zero recurring fuel costs.
That's a huge chunk of the electric bill just gone. Right there. So what about the cooling?
The vacuum of space is a perfect natural heat sink. It's just cold. So you can dissipate the waste heat from the AI chips using simple passive radiators. You're not using expensive liquid chillers or consuming vast amounts of water.
Another huge OpEx saving.
A very substantial one.
Okay. I get the huge savings on the electric and water bill once it's up and running, but given that 5 to 10 times premium, how many decades does it take for those OpEx savings to even break even on the CapEx?
And that's the critical question. The math suggests that for just, standard bulk compute, the break-even is way too long. The solution isn't about saving money.
It's about buying something you can't get on Earth.
Exactly. It's about accessing unique benefits.
Oh, what are they? What are those benefits?
First, scalable modularity. Instead of a massive civil construction project for a new data center on the ground, adding capacity is done by just launching another satellite.
So you can grow in smaller steps.
Much smaller. You can increase compute capacity in, say, 10 or 50 kilowatt increments as you need it. It's much more flexible.
And what about global access? How does this change things?
It changes everything. A satellite constellation can provide compute anywhere that satellite is visible, so you're covering roughly 50% of the planet at any given moment.
Which offers built-in resilience.
Unmatched resilience. If a terrestrial grid fails, or a disaster takes out a regional center, the compute just automatically shifts to the orbiting nodes. It's global redundancy.
So if that physical separation helps with disasters, does that isolation also mean better security?
Absolutely. Security through isolation. Being physically separate from local networks on the ground significantly reduces the risk of large-scale attacks like ransomware that spread through networks.
It's hard to hack something that isn't plugged into your local grid.
It's very hard.
Okay, here's where it gets really interesting for me. The future of autonomous systems. I'm thinking of autonomous shipping, massive drone fleets, things that need instant AI support far from the nearest city.
And that's where this idea of a cloud in the sky becomes a reality. On-orbit AI can provide model inference or updates with almost no backhaul latency.
So the drone just pings the nearest satellite.
Exactly, and you're looking at response times under 10 milliseconds.
That's faster than a terrestrial fiber connection from, say, New York to California.
It is. And the final strategic benefit is sovereign compute. A nation can launch its own assets, its own data center, guaranteeing that its most sensitive models for intelligence, for defense, never touch foreign soil.
You control the hardware completely because it's literally flying over your head.
You have total physical control, an extreme level of trust.
Okay, so that's the dream scenario. Unmatched efficiency, global reach, total security. But now we have to deal with the reality. The CapEx is astronomical. So let's dig into the hurdles, starting with that launch cost.
We have to quantify it. Right now, launch prices, even with a reusable Falcon 9, are about $2,500 per kilogram.
$2,500.
So a single 10-ton AI satellite, which is actually pretty small for a data center, that could cost anywhere from $25 to $125 million.
Just for the launch.
Just to get it up there. Even with the most optimistic cost projections for new rockets, the investment barrier is just immense.
So the minute it launches, a huge clock is ticking on that investment. And what kind of technical hits do you take once you're actually operating in space? Let's talk about radiation. Soft error rates. What does that actually do to an AI model?
What's really important here is that cosmic rays and solar particles are constantly bombarding the chips up there. And this can flip a binary bit. A 1 becomes a 0.
A soft error.
Right. It doesn't physically break the hardware, but it corrupts the calculation. If that happens while a large language model is running, the entire result can become meaningless.
So what does that mean for the workload? What do you have to do?
It means you have to use extensive error correcting codes and constant checkpoint restarts.
Like saving your game every 30 seconds.
Sort of. Think of it as the computer constantly having to pause the AI's work, check if the numbers have been scrambled, save its progress, and then resume. You're burning valuable compute cycles just managing errors, which reduces your effective performance.
And that leads right into the next problem. Obsolescence. On the ground, you can swap out GPUs every few years. You can't just drive a forklift up to a satellite.
Precisely. Without a mature on-orbit servicing ecosystem, which we don't have yet, the hardware is write once, fly once, and because AI hardware gets better so fast...
Moore's Law.
Right. The obsolescence cycle in orbit is much shorter. We're talking 3 to 5 years. So you launch it, and in a few years, it's already lagging way behind ground-based systems, and there's nothing you can do about it.
Let's talk about the infrastructure bottlenecks. I mean, training these huge models requires petabytes of data. How do you get it up there or get the results back down?
Is a severe constraint. Even with these super high-capacity laser links between the satellites, the final piece of the puzzle is the downlink to ground stations.
The last mile. Or the last few hundred miles.
Exactly. And that ground segment bandwidth creates a major bottleneck. You might have all this compute power in orbit, but you just can't feed the beast fast enough.
So your data is either stuck in orbit or stuck on the ground.
Yeah, and then there's power density. For the really demanding stuff like high throughput training, the instantaneous power you have is limited by the size of your solar panels and your batteries.
You can't just plug into the grid for a power surge.
There is no grid. So these multi-megawatt training sessions, which are common on Earth, they're just not feasible today in orbit. It really limits the kinds of jobs the orbital center can do.
We also have to touch on the environmental impact paradox. We praise the zero carbon operation, but what about the launch itself?
It's a huge offset. It really is. While the data center's operation is clean, each launch contributes significantly to emissions. A single Falcon 9 launch, for example, emits about 300 tons of CO2.
And you'd need a whole constellation of these things.
A large constellation, yeah. So those launch emissions could potentially negate the climate benefits you gain from the solar power and passive cooling. The overall carbon footprint becomes questionable.
Okay, so let's recap this section. It's 5 to 10 times more expensive, and it has built-in performance penalties from radiation and obsolescence, plus data bottlenecks. So this means we have to find applications where speed or secrecy or survivability is so valuable that it makes that huge cost worth it.
Absolutely. The value proposition has to outweigh that premium. And the sources we looked at identified 5 true killer apps where the benefits really seem to hold up against the cost.
What's the first one?
Global real-time satellite image analytics.
Okay, so that's for disaster response, military surveillance.
Right. The processor happens in orbit right next to the sensor. You eliminate the need to downlink petabytes of raw imagery. Instead, you just send down the actionable intelligence, the answer.
The AI is a filter in the sky. Got it. What's number 2?
Edge AI for fleets. We touched on this. Providing model updates to autonomous ships or aircraft with that guaranteed sub-10 millisecond response time anywhere on the planet.
Something no terrestrial network can promise.
Can't even come close.
The third is the big strategic one. Sovereign AI for defense and intelligence.
This is critical for national security, a secure compute cloud where a country's most vital models are guaranteed never to be hosted on foreign soil. It gives you a level of physical and regulatory protection you just can't get otherwise.
And the fourth application is for science.
Space-based scientific computing, yeah. Co-locating compute with a sensor, like a huge orbiting telescope. It lets you do in-situ data reduction.
Again, you're not trying to downlink massive raw data sets.
Exactly. You save billions in ground infrastructure and years of time.
And the final justification.
Redundant global backup. Basically offering resilience for a nation's critical AI services against any kind of widespread terrestrial outage. A major grid failure, a natural disaster, it's insurance against a worst-case scenario.
It really seems like every single one of these use cases is defined by the fact that you can't solve the problem any other way.
That's the common thread.
Before we wrap up, let's briefly touch on regulations. Building on the ground requires permits. What's the red tape for building a data center in LEO?
Oh, the regulatory hurdles are immense. You need to get access to already crowded orbital slots in LEO. There's a strict requirement to have end-of-life deorbit capability to deal with space debris, which adds mass and cost.
Plus insurance, I imagine.
Huge insurance. And you need to get the right frequency allocations for your ground communication so you don't interfere with other vital satellite services. It's a minefield.
Okay, so let's bring this all together. We started with the question, is orbital AI a dream, or is it a practical solution?
And I think the synthesis is that it's both. Orbital AI clusters offer this unmatched global reach and ultra-low latency, but only for very specific workloads.
Because the economics are just brutal.
5 to 10 times higher. So it is highly unlikely orbital centers will ever fully supplant terrestrial ones, not for bulk compute.
So what does this mean for the future of AI infrastructure? What's the long-term outlook?
I think the most probable scenario is a hybrid approach. Terrestrial centers will continue to handle the bulk of the work, the heavy training, the high-power stuff where low cost per operation is everything.
And the orbital centers.
They'll serve those specialized high-value applications where guaranteed speed or secrecy or global availability outweighs that 5x to 10x cost premium.
The right tool for the right and extremely expensive job.
So if we accept that the future is hybrid orbital nodes for only the highest value cases, we want to leave you with this final provocative thought. Think about the terrestrial AI application you or your organization relies on most today. Which part of it is currently slow enough or insecure enough that you would instantly pay a 5 to 10 times premium to guarantee its speed, privacy, or global availability? Because that is where the investment is going to go next.
Until next time, keep exploring, keep questioning, and keep diving deep. Thank you for listening to today's podcast. Please feel free to click on the link in the description below to discover more podcasts.